The following presentation is entitled Classification Trees. Classification trees are a simple natural structure for classification that is widely used in machine learning and artificial intelligence. So the training objectives for this presentation are to define a classification tree and to apply a conventional learning algorithm. The presentation has been structured according with these two objectives. Well, so what a classification tree is? It is a hierarchical structure for the classification of objects. So, for instance, let's see this example in which objects are defined as two-dimensional vectors having two features, two real features. So we are representing the objects here. This is the first feature, this is the second feature. And what a classification tree looks like for this case. So it looks like this example. We have nodes, this is internal nodes, and we have leaves here. And internal nodes are labeled with a criterion to build a classifier, the tree classifier. Here what we check, conventional test is to check whether a feature is less or equal than a certain value, for instance, x1 minus or equal to 3.5. Here we have another test, x2 minus or equal to 5. And then if the answer is yes, we go over the left branch, and if not, the right branch. So what is the effect of classification tree is that it builds, it partitions the representation space of our objects in rectangles, or in general hyperrectangles in more than 2 dimensions. Here we have, for instance, this blue rectangle here corresponds of all objects having more than 3.5 for feature 1, which is this leaf here. And then for the remaining objects, all having less than 3.5, we have this area here, and it is divided in 2 parts, which corresponds to objects that have a feature, a value for the feature 2 larger than 2.5 or smaller. So this leaf corresponds to this rectangle, and this leaf corresponds to this rectangle. Okay. How classification tree is learned? It can be provided by an expert knowing the task, or it can be learned automatically from data. This is the approach we follow here. We build a classification tree following this algorithmic scheme. It's a, let's say, generalized scheme. I mean, it's only the main aspects of a classification tree learning algorithm. Okay, we see how it works. Let's see how it works. We are given a set of training samples and training samples. And what we do is we dichotomize first. What we do first is we dichotomize S by applying a certain criterion and dividing S in that way into a left branch or left subset and a right subset, and achieving a certain decrease of impurity delta I. Okay, so here it's well described what this function does. Dichotomize divides the set S into 2 subsets L and R, applying a splitting criterion C with which a decrease of impurity delta I is achieved. Okay, we also use a epsilon value as a threshold of impurity. So if the decrease of impurity is below a certain minimum threshold epsilon, then we decide it does not pay off to further divide the given set into 2 branches, and we return the given set as a leaf for the tree that is being built and label according to the mode in the given set. I mean the most frequent label in the given set. Otherwise, it is considered an internal node of the classification tree, And what we return is an internal node with no class level, a criterion to split the data at that internal node, and we build the left branch by calling recursively to this function with the left subset and analogously for the right branch. Okay, for the splitting criterion, by far the usual approach consists in selecting a variable threshold pair, the R, and divide the dataset as follows. Left is all training samples having in feature D a value less than R, and right is all the remaining samples, all samples having in feature D a value greater than R. So for instance, in this case, if we consider these 4 points, and we consider this the pair dimension 1 and the value R threshold 3.5, for these 4 points, we would check this feature and this threshold, and those on the left will be included in the L subset, and those on the right on the R subset. Okay, so we have many potential future threshold pairs to consider, and we need to check at when we build the classification tree. We need to decide which pair we choose. So for this, it's convenient to introduce the concept of impurity of a node T. It is the uncertainty of the class of the objects in T. And usually it is computed as the entropy of the empirical distribution of the class posterior probability in T. That is, the impurity of a node T is minus sum over all classes of the empirical posterior probability for class C times the binary logarithm of this value, where the empirical posterior probability for class C in node T is the number of samples from class C in node T with respect to the total number of samples in node T. So here I have an example for the root node here that includes all samples. We have one sample from class 4, so it's 1 over 4 binary logarithm times binary logarithm of 1 over 4 with minus in front. And then for the blue class, we have 3 over 4 binary logarithm of 3 over 4 with minus again, which is 0.81 impurity. And then for this internal node, T1, which is this one, we have one sample for each class, so we have minus 1 over 2 binary logarithm 1 over 2, and again minus 1 over 2 logarithm binary of 2 1 over 2, which is 1 over 2 plus 1 over 2, that is 1 here, impurity. And for those nodes, the leaf nodes here, all of them, where there are only samples, training samples from only one class, the impurity is null. So, okay, this is the idea. When we need, when building the tree classifier, we need to decide which feature and threshold use in order to build the tree in an internal node. We decide according to this criterion, maximum decrease of impurity. So for all pairs, the R, we choose the pair having maximum decrease of impurity. Maximum decrease of impurity, where decrease impurity is the impurity of the father, of the parent node, minus the impurity of the left node, and minus the impurity of the right node, and in both cases weighted by the number of samples in the left node with respect to the total number of samples on the right node, analogously for the right node. So for instance here, the impurity, when we build this tree classifier, here is the impurity of the parent node is 0.81. We have seen how to, the previous slide, we have computed it here. And then the left node has impurity 1, which is this one here. We have computed here, T1. And the right node has impurity 0, so it is impurity of the parent node minus 2 over 4 left, minus 2 over 4, impurity of the 4. So the decrease in impurity is 0.31. Okay, so this is the way we build the tree classifier, and in conclusion, we have seen what a classification tree and how to learn it with a conventional technique, and this ends the presentation.